Hello, sir.
Yes.
Please, can you repeat what you just said about concentration of acid equals to concentration of conjugate base? I didn't really get
I
you this.
would go into that fully now. So do you understand? I'll repeat it.
Okay, sir.
I'll repeat it shortly. I'm going to show you an equation. It's already recorded. So I'm sharing my screen. I hope you can see my screen now.
Yes,
Yes,
I don't want
sir.
to mute you all.
Yes, sir.
Okay, so
Yes, boss.
please just mute yourself. Everybody should mute themselves. Don't let me mute you. So I said something about the pK being the pH at which the concentration of acid is equal to the concentration of base. So essentially, when you have the two at equimolar concentration, you know, there will be a point when the acid dissociates into conjugate base. And as this dissociation continues, at a point in time, the concentration of the base and that of the acid will be equimolar concentration. So at that point, it could be said that what? It could be said that the pH at that point is equal to pKa at that point. So if you look at the Henderson-Hasselbalch equation, let me get my controls back. So I'm using your. So if we look at the Henderson-Hasselbalch equation, states that the pH equals pKa plus log of base over acid. So the Henderson-Hasselbalch equation describes the behavior of weak acids and buffers. I already told you that a weak acid has buffering capacity because the buffers are composed of weak acids and the salts of their bases. So the weak acid has some buffering capacity. If an acid HA ionizes, it will ionize into hydrogen ion and the conjugate base. The conjugate base here is A minus. If we extrapolate that term, we could get the Ka for that. That's the equilibrium constant for this acid dissociation will be Ka equals hydrogen ion multiplied by A minus concentration over HA concentration. So if we do some manipulations, we could get the term pH equals pK plus log of the conjugate base over log of the concentration of the conjugate base over concentration of the acid. Now look at this situation where, so this equation is the Henderson-Hasselbalch equation, and it describes the behavior. It shows the relationship between pH, pKa, the concentration of your base and concentration of the acid in that solution. Now, if just assume that if you have the conjugate base and the conjugate acid here, the conjugate base and the conjugate acid, if they are at equimolar concentration, A minus over HA, that will be if you divide the equimolar concentration, you get 1. So pH will be equals pKa plus log of 1. Log of 1 is 0. So that means the pH is equals to pKa when the base and the acid are present at equimolar concentration. I think that explains what the student in question asked earlier. Now, when an acid is exactly half neutralized, what you have is that the acid and base will be present at equal concentration, So you have the pH equals pK plus log of 1. Hence, the pH will be equals pK plus 0. So the pH will be equals to pK. So I said something that pK is the negative log of Ka. It is also the pH when the concentration of base and acid are equal. It is equally the pH when an acid is half neutralized. When the acid is half neutralized, that means half of the acid has undergone neutralization reaction with a base. Now, also, if we take the Henderson-Hasselbalch equation, we could look at how the pH behaves when the concentration of base and acid change. So essentially, the Henderson-Hasselbalch equation will tell us how the pH will change when the concentration of acid or base changes. Now, without much ado, if the acid and base concentration are the same, we say that the pH equals the pKa. Now, what about when you had more acid? If you had more acid, that means the pH will do what? The pH will reduce. If you had more base, the pH would increase. This equation shows all that. So if you have an increase in the concentration of the acid or base, it will change the pH, as you can see from this equation. So when the ratio of the ratio of conjugate base to acid is 100 to 1, that means you have a low concentration of the acid. What you expect is that the pH would increase. So you have a pH, the pH equals pK plus 2. Now, what about when the ratio of acid to base, the ratio of the conjugate base to acid is 1:1? That means you have more acid. So when you have more acid, you also expect that the pH would reduce. The pH will reduce. More acid would bring the pH down. So this equation is true for acids. So it is true for acids. It shows us the relationship between the pH, pK, and the concentration of base to acid. So buffers and buffer systems. There are two main types of buffers that you find in the body. You have the bicarbonate buffer, which has a lot of buffering capacity in the system, and you also have the non-bicarbonate buffer systems. The solution of weak acids and their salts buffer changes in pH. The solution of weak acids or bases and their conjugate base or conjugate acid would exhibit buffering. Their ability to resist the change in pH following the addition of a strong base or a strong acid is buffering. So many metabolic reactions are mostly accompanied by the release or uptake of protons. Most intracellular reactions will be buffered. So we have natural buffers in the human body that tend to help with regulating the pH so that you don't have acidosis or alkalosis, Hence, there are lots of molecules designed to carry out buffering ability. So the mechanism of pH control. So buffer system consists of a weak acid and its anion, or what you call its conjugate base, the salt of its conjugate base. There are three major buffering systems. You have the protein buffer system, which is made up of the amino acid. The functional groups of the amino acid, as you know very well, have the carboxylic group and the amino groups. And these are groups that can take up protons or donate protons. So if they are able to take up protons and donate protons, they are able to exhibit buffering capacity. The hemoglobin buffer system too is also able to buffer. you have the carbonic acid bicarbonate, which buffer changes caused by organic and fixed acid. So the other, apart from the protein and the hemoglobin buffer system, the other minor buffering system we have is the phosphate buffers. The phosphate is part of the backbone of our nucleic acids. So we have a lot of nucleic acids in living organisms. Now, these living organisms, their phosphate group, the phosphoric acids there, also tend to help buffer pH in the intracellular fluid. So there's a relationship between the partial pressure of carbon dioxide and the plasma pH. So it says that where you have as a partial pressure of carbon dioxide rises, the pH would fall. So I would explain using the bicarbonate buffer system. So these are some of the buffer systems in body fluids. The intracellular fluid has the phosphate buffer as well as the protein buffer, but the extracellular fluid also has the protein buffer, and the extracellular fluid majorly has the carbonic acid bicarbonate buffer system. So the protein buffer, it's composed of three main components. Hemoglobin, which is made up of the globin protein, is also able to serve as buffers. The amino acids in all proteins are also able to serve as buffers because of their carboxylic and the amino terminal ends have buffering capacity. So there are also some plasma proteins too, because you know they're also composed of amino acid. They're also able to carry out buffering in the body. So the protein buffer system, if pH climbs, that means if the pH increases, then tending towards basicity, the carboxyl group of amino acid will act as a weak acid and donate some of its proton so that it will bring down the pH. So if the pH also drops, the amino groups would act as a weak base and take up what? Proton. So if the pH drops, whereby you're having more hydrogen ion in that solution, the amino group will take up some of this hydrogen atom and act as a weak base to mop up the hydrogen. So hemoglobin buffer system too, it prevents pH changes when the partial pressure of carbon dioxide is rising or falling. Now, this is how the amino acid act. So if pH rises, you know very well that the amino, we said that the carboxylic group will act if pH rises. Right? If pH falls, the amino terminal will take up hydrogen, the protons. So you have these two conditions. So in alkaline medium, the amino acid acts as an acid and releases its hydrogen or the protons from the carboxyl terminal, while on the other hand, if the pH falls, the amino terminal would act, the amino acid will act as a base using its amino terminal to absorb proton. So the carbonic acid bicarbonate buffer system, there are three equilibriums that exist there. Carbon dioxide will dissolve or would react with water to form carbonic acid. The reaction there is catalyzed by carbonic anhydrase. Now, at the same time too, carbonic acid can be degraded. It is still catalyzed by carbonic anhydrase, can be degraded back to produce, or it can be broken down to produce carbon dioxide and water. Now, however, the carbonic acid, if it is not acted upon by carbonic anhydrase, the enzyme carbonic anhydrase, the carbonic acid can give up its proton, depending on what happens to the pH, can give up its proton. It can give up its proton when the pH increases. When the where the pH increases, it gives off its proton to bring down the pH level. So on the other hand, too, where the pH reduces to, it could also take up some of this proton using its bicarbonate. So the bicarbonate there should be HCO3 minus. Now, however, the carbonic acid bicarbonate buffering system has the following limitations. It cannot protect the extracellular fluid from pH changes due to increased or depressed CO2 levels. It only functions when respiratory system and control centers are working normally. So it is also limited by the availability of bicarbonate ion. So if the bicarbonate reserves are low, you don't have much buffering from the bicarbonate buffer system. Now, this is a depiction of what happens. The carbon dioxide and water react to form carbonic acid, and the carbonic acid can go into equilibrium. An equilibrium reaction can produce hydrogen ion and bicarbonate ion. So the bicarbonate ion is mostly gotten from bicarbonate receptors to produce more carbonic acid if there are excess hydrogen ion within the system. So the fixed acids and organic acids when they add hydrogen ion, the bicarbonate from the reserves can pick up these hydrogen ions and then increase the level of carbonic acid within the body. And this carbonic acid can then be degraded into carbon dioxide and water. And carbon dioxide is released via the respiratory system. So you know very well that that's reaction whereby carbonic acid is converted into carbon dioxide and water is catalyzed by carbonic anhydrase. So now, maintenance of acid-base balance. The lungs help regulate pH through carbonic acid bicarbonate buffer system. So changing respiratory rates would also change the partial pressure of carbon dioxide. The kidneys also help regulate through the renal compensation through ion exchange. They are regulating the ion level, the bicarbonate levels would also help regulate pH. So I want to thank you for listening. We'll continue our class. So we'll continue the class later.